Now we're going to begin going through what this logarithmic function is, and we're going to start by going through that and its properties. So first and foremost, we're going to go through how we define this logarithmic function. We've dealt with special bases for the exponential, so we're going to do the same thing with the logarithmic. Then we're going to go through properties of logarithms in the same way we have properties for exponentials. And then we're going to talk about something that's called our change of base formula. So first and foremost, we know y equals b to the x is a one-to-one function. So it has an inverse. It passes the horizontal line test. If you think of its graph, it looks something along the forms of this, or it looks like this, just depending on the actual value of the base. Both of these, however, pass the horizontal line test. So we know it has an inverse. The problem is if I try to go through switching my roles of x and y, I have to solve where does x equal b to the y. And I have no way to know how to solve for this exponent spot here. So that's where we define this logarithmic function. So the inverse of the exponential is the log function, which is denoted by y equals log base b of x. So this base b here is the exact same base on that exponential function, okay? So when we talk about converting or talk about working with this logarithmic function, it's really going to be useful to kind of switch it to its exponential form because we're always going to be able to go back and forth between the two. So the way we define this logarithmic function is we go through and we can write it in its equivalent exponential form. So the way this is defined is our base is b. This is the input of the logarithm, so it's the output of the exponential. And then the output for the log becomes the input for the exponential. So it switches those roles of x and y when we go back and forth between these two. So there's another way you can also go about working with this. So I learned this phrase in high school. There's a couple different ones, but I always learn this as bacon and eggs. So if I have some logarithm, bacon is b, so it's the thing that comes first. We want to put it where our base is first. So if I want to convert this logarithm to the exponential, my phrase is bacon and eggs. So there's three components that switch in going to the exponential form. So the bacon is the base. So in the equivalent log form, my base is b, and I'm still writing an equation. My end stands for the answer. So this becomes the answer in the exponential. And the eggs is the exponent. So my exponent here is y. So I can always convert back and forth. I can start with exponential and go to log, or vice versa. The other thing that also might help you kind of keep track as to how certain things convert, it kind of looks like this is an exponential. It kind of looks like it's b to the x equals y. There's no way I can just get rid of this log and have b to the x equals y. Something has to switch. So the x and y, or input and output, flip-flop roles. Okay. So let's just get some practice putting things in other forms. So we're going to start by rewriting in its equivalent exponential form. Okay. So based on this, my phrase, my bacon is my base. This is the answer and the exponent, bacon and eggs, or you can use bay to remember this, right? But in the equivalent exponential form, my base would be 2. My answer is 32, so you notice it looks like 2 to the 32 here. I don't put 32 in my exponent spot. Instead, the output goes to the input. So this is the same thing as saying 2 to the 5th equals 32. Okay. Same thing for this next one. I start with a log. So my base is the thing that looks like it's in the base position. this becomes my answer, and this is my exponent. So these two flip-flop spots in the exponential. So in its equivalent exponential form, this is 1/4. My answer is 64, and my exponent is -3. And you could check if both of these are a true statement. Okay. Now let's try the other way. Let's put this in its equivalent log form. So when I start by writing this out, I start with log. My base is 3. So this is log base 3. My answer is 81. So 81 goes inside the logarithm. And my exponent is 4. So that goes on the opposite side of the equation away from the 3. Even though the 3 and the 4 are paired together, it switches where it's near. And now same thing for this one. The only difference is I don't really have an exponent, but remember a square root you can rewrite. This is the same thing as saying 169 to the 1/2 is equal to 13. So putting this in log form, my base is 169, my answer is 13, and my exponent is 1/2. So that is its equivalent log form. Okay. So when we're dealing with evaluating logarithms, it's going to be really difficult to do this within your head. It's not something that's going to be clear cut because this is a brand new operation and a brand new function that we're defining. So a lot of times what's going to be really beneficial whether I'm evaluating a log or whether I'm solving a log equation is turning it back into its exponential form. Like this one, if I try to evaluate log base 5 of 1, I have no idea what that is off the top of my head. The only thing I do know is this equals something. So I'll say it equals x. What I can do now is I can turn this into exponential form, and I want to figure out what does x equal. Okay. So re-putting this in exponential form, my base is 5, my answer is 1, and my exponent is x. And so looking at it in this form, I now know the only value I could plug in that makes this a true statement is if x is equal to 0. Okay. So what that means is when I'm taking log base 5 of 1, it equals 0. Okay. Same thing for this next one. I cannot do this just using my brain. It's not possible for me to kind of visualize what's going on here. So I'm going to put this in exponential form to be able to evaluate what my x has to equal. So my base here is x, my answer is 81, and my exponent is 4. So if I want to solve this for x, I'd have to take a 4th root. And remember, anytime you take an even root, you technically get a plus or minus. But this is the base. Remember, we don't want a negative base. So I really only consider the positive one. I don't need plus or minus. And if I take the 4th root of 81, that would give me 3. So the value of x that solves this equation is going to be 3. Now, if you take a look at any type of handheld calculator, so we can use a scientific calculator in this class. Yes, while you're doing your homework, you have access to online calculators, which have way more capabilities. But on any standard scientific calculator, you're only going to see 2 buttons. You're just going to see log, and you're going to see this ln. Both of these are just special logarithms, so they get special notations. So if you see log without any base, it's really meaning that it's base 10. And when you have natural log of x, it means your base is that natural base of e. So this top one is called our common log. And this bottom one is called our natural log. And hence the ln. So this often gets confused for a 1. It's not I tend to like writing these in cursive myself. ln is what that means. So let's try some examples. Let's approximate with a calculator if possible. So I'm going to pull up my calculator app that I have on my iPad. So for these, if I scroll through my function features, I have quite a few. This one does have a special base of 2. And then I have this log with the 10 there. If your calculator doesn't have a 10, that's okay. Just log means it's base 10. And then I have my ln button over here. So I want to evaluate these to we'll do to 2 decimal places just to be safe. For the first one, what I have to do is I have to input, let's see if I can get this. I have to input my inside first, and then I press my ln button. So ln of 31 is going to be about 3.43. Okay. If I want to do log of 412, I've got to do my inside first. Again, your calculator could be different, but log just means log base 10. So log of 412 is about 2.61. Okay. If I tried to do log of 0, I would do 0 and ln. And this is where it gets kind of funky. You really don't get an answer for this. So if you try on a handheld, what you're going to see is an error button. This is actually undefined. And then same thing if I try to do -2. So I think I have to do this first. Nope. There we go. I have to do 2. I've got to make it negative. And then if I try to hit the log button, now I'm getting a much easier clear. This has an error. So this is also undefined. Okay. We're going to talk more about the domain of the logarithmic function. But remember, for the exponential, your range was 0 to infinity. So that means that's the domain for the logarithmic function. I need the inside to be positive. Okay, so this is going to pose a little bit of issues when we have to try to evaluate things other than base 10 or base e. So we'll see some at the very end how we can go about that. But before we get to that, just like we have all of our properties of exponential functions, we have properties for logarithmic functions. So this beginning setup just kind of sets everything to make sure that I'm not taking log of 0 or log of a negative number. Remember, my base, I want to be a positive number, and a base of 1 is boring. So I'm going to try to translate all of these to those exponent rules when possible. But for this first one, if I try to take log base b of 1, it's going to end up always equaling 0. And the reason for that is we can look at its equivalent exponential form. So this is because my base is b, my answer is 1, my exponent here has to be 0. So anytime I have a 1 inside my logarithm, the output of it is 0. For the second one, if I want to try to figure out what it equals, my base is b, my answer is b, I'm looking for the exponent spot. The only thing that makes sense in this equation is 1, because b to the 1 is 1, right? When I deal with multiplication inside a logarithm, remember our exponent rule was when we multiplied stuff with the same base, we added the exponents. It's the same kind of rule here. It's going to split as addition. Okay. So when we have multiplication, it splits for logarithms through addition. And then in the same way, if we have subtraction, if we have division, it's going to split to subtraction. So I'm going to get log of the numerator minus log of the denominator. If we have a power, so remember if you took an exponent, a power to a power turned to multiplication, what's going to happen here are the powers pop out front. So this is going to be the power times log base b of m. Okay. So these three rules all just follow from our exponent rules. The next two are going to follow from the fact that the functions are inverses of each other. So if you think of taking the cube root of x cubed, it cancels and gives you x. And then in the same way, if I cube the cube root, they cancel and give us x. So when I'm dealing with my log and exponentials evaluated at each other, because they're inverses, they're going to cancel. So if I have log base b of b to the x, all of this is going to cancel out, and it leaves us with x. And then same thing here, if I have b raised to the log base b, they're going to cancel and give us x. There is one slight stipulation here because you have log base b of x. This only works when x is a positive number. Okay. So let's try some examples now. Evaluating these logarithms. If you aren't comfortable memorizing the properties or they're not clicking, remember you can always say this is equal to x and solve its corresponding equation. But based on our properties, if I have 1 on the inside of the logarithm, this is always going to equal 0. And I can check myself by putting it in exponential form. This is the same thing as 5 to the 0 is equal to 1. Okay. For my next one, I have log base 9 of 9. Remember, you can think of this in two ways. As our second property, log base b of b is always equal to 1. Or because the base on both of these matches up, you get the exponent. And the exponent here is really a 1. But we can also check that this is right. My base is 9, my answer is 9, and my exponent is 1. For this next one, we have ln of e to the 4th. And remember, ln just means log base e of e to the 4th. So in the same kind of manner, we've got the same base on both of these. They're going to cancel each other out, and it gives us 4. Okay. For this next one, because I have just log, it means it's base 10. Same idea, these two cancel each other out, and it leaves us with x plus 3. Okay. So before we jump into actually solving equations involving these, which is definitely more complicated, we want to really solidify that we can manipulate these log expressions. The more you do these, the more steps you're going to be able to skip, but I would say put as many as you need starting out. So for this very first one, the very thing I notice first is I have something times something inside my logarithm. So my property tells me that I'm going to be able to split this as log of the one plus log of the other. Okay. With these, it's definitely hard to figure out when you need to stop, but pretty much if you can apply a property, apply it. So here I now have log of square root of a and log of 5th root of b. Technically for both of these, I can turn these into exponents. So this is a to the 1/2 inside the first log, and the 5th root turns to a 1/5 power. Okay. And now my other property of logarithms are that these powers pop out as multiplication. So this is really equal to 1/2 log of a plus 1/5 log of b. Okay. For this next one, again, I'm going to put more steps than is necessary, but we'll kind of talk at the end as to what we can do to simplify this. So I technically have multiplication in here, but I also have division. So I'm going to start with this division. So we can split division through subtraction. This means we get ln of our numerator minus ln of the denominator. Okay. And now I can go through and split this even more because now I have multiplication within here. So this is really equal to ln of x minus 4 squared plus ln of x minus 1 cubed minus ln of x plus 2 to the 5th. Right. And now there's one last step. Each of these on their own has an exponent, so they can pop out front. So the furthest we can expand this is 2 times natural log of x minus 4 plus 3 times natural log of x minus 1, and then minus 5 times natural log of x plus 2. Okay. So what's going to happen with these is when I have pieces in the numerator, they're going to be positive, so they're going to be through addition. When I have pieces that are in the denominator, those are going to turn to subtraction. Right? If I had multiple pieces in the denominator, they would all be negative to indicate that it's division. So let's try another example now that does have multiple negative pieces. And again, we'll add more detail within it. But you're going to see both of these negative pieces are going to end up in the denominator. So I really can kind of shortcut and say the things that are positive go in the numerator, things that are negative go in the denominator. But before I can start condensing this, the one thing I have to do is I have to push all of these constants out front because it has to be ln, ln, ln. I can't have this 1/2 or 1/3 out front. So my first step is to pop these in. So this would be x plus 3 to the 1/2 minus ln of x plus 2 to the 1/3 minus ln of x. Okay. And then the other thing I'm going to do, just so I don't have to keep writing these, this is ln of the square root of x plus 3 minus ln of the cube root of x plus 2 minus ln of x. So I'm going to start with just the first two pieces. I have natural log of this minus natural log of this cube root. So that's going to condense as division. So this is equal to natural log of the square root of x plus 3 divided by the cube root of x plus 2. And then from this, we're going to subtract natural log of x. So again, this is going to become division. So the problem is you end up creating some complex fractions. I have this first fraction, and then I'm dividing it by x, okay? Because it's natural log of this minus this, so it's natural log of this fraction divided by x, all right? But to actually condense this, really I'm going to do this off to the side to make it a little bit cleaner. If I'm taking the square root of x plus 3 over the cube root of x plus 2, and I'm dividing it by x, it's the same thing as taking this and multiplying by the reciprocal. So ultimately what happens is this becomes natural log of the square root of x plus 3, and then I get both of these factors in the bottom. So we're going to have x times the cube root of x plus 2. Okay. So again, you really can kind of skip these intermediate steps. The positive thing stayed in the numerator. The negative pieces went to the denominator. So the very last thing we're going to do is we're going to go through how I can evaluate something other than base e or base 10 in our calculator. So I have to be able to write it in terms of one of those bases to be able to input it. So we're going to try to evaluate log base 4 of 3. And so what I'm going to do is really just a lot of manipulation. Log base 4 of 3 is just a number. So I'm going to call this number y. Okay? If we go ahead and we rewrite this in exponential form, my base is 4, my answer is 3, and my exponent is y. And my goal is to basically find another way I can write y. And that will tell me it's equivalent to log base 4 of 3. So at this step, what I'm going to do is if these two sides are equal, then when I take natural log of this side, it better equal natural log of this side, right? So let's do numbers just so you can see like why that's true. 5 is definitely equal to 5. So if I take natural log of 5, it's equal to natural log of 5. I can take natural log of both sides. Right? But the reason for doing this is if we have natural log of 4 to the y, that equals natural log of 3. I now have this y in a power spot. It's going to pop out. So this is the same as y times natural log of 4 equals natural log of 3. Okay? And my goal is exactly to rewrite y. So at this stage, what I'm going to do is I'm going to take both sides and divide by natural log of 4. And this tells me my y is also equal to natural log of 3 divided by natural log of 4. Okay? So y can be rewritten as this. So this means log base 4 of 3 is equivalent to natural log of 3 divided by natural log of 4. At this stage, instead of taking natural log of both sides, I could have taken log base 10. And the only thing that would have changed is down here, instead of having natural log, I'm going to have log base 10. So this is also equal to log base 3 over log of 3 over log of 4. So we can actually plug these into our calculator. So I'll try with ln of 3 over ln of 4. So we do 3 natural log, and then we're going to divide that by 4 natural log. And this gives us, it's about 0.7925. Okay. And if I do the other way, let's clear it. If I do log base 10 of 3 and divide that by log base 10 of 4, you end up with exactly the same answer. So it doesn't matter which one you use and plug in your calculator. So in general, this is what our change of base formula says. If I have log base b of m, the base goes in the bottom of either of these logs. Doesn't matter which one you use. Okay. So for this example, if I try to do log base 3 of 35, you can write this as log of 35 over log of 3. Or you can write it as ln of 35 over ln of 3. But either way, if you plug this into your calculator, you should see this is about 3.2362.